when I saw that there was a LoRa paper, I had to make a video about it. This one's especially cool because so we have LoRa that can help you fine tune. We have LoRa that can help you fine tune with even smaller parameters, quantized LoRa, and now we have LoRa that can do pre-training, which is what this paper proposes. They propose a method to use LoRa to pre-train models, and the goal is to basically do it without using full rank matrices. So pretty cool paper. This one was pretty enjoyable to read. Um, Also a pretty cool idea. So let's get into it. So first off, we quickly mention LoRa. We all know and love LoRa, but quickly mention it. So basically, you have your matrix here. This is your matrix X, and it is of shape, say, T by E. This may be your time. Uh, so this is your time embed, and this is your embedding space. So this may be a sequence of words or something like that. And what you usually have is you usually have a weight matrix, which transforms this from E to E. So you would feed your input through the weight matrix, or the linear layer, the affine layer, whatever, and you get out your new matrix Y, which is of shape T by E. Now, this output matrix is what you normally get if you just do normal pre-training, and the idea with LoRa is we can fine-tune our large language model after it's been pre-trained with this full rank matrix, which is E by E, using small matrices. So we would have a matrix A, which goes from this matrix would be of shape E by R, and then you would get out this little matrix here, or yeah, it would be small like that, which would be T by R, and then you would feed that through another matrix B, which would be of shape R by E. So just flipping it where R is significantly less than E. And whenever you're doing this training, you would freeze, that is the wrong panel, you would freeze this weight matrix, so you don't have any you don't have any like, atom moments you have to worry about. You can also quantize this to make it even smaller. So these weights are really small, and the weights that you train, you don't have a lot. And if R is 1, so at the smallest case, if R is 1, then you just have 2E weights that you have to train, rather than this full E by E, which is E squared. So it's a big difference, and you can kind of change this up by changing R. There's kind of been some other this like you can kind of weigh this uh, these new LoRa weights as well. So whenever you train them, you can then recombine them into W, and you do that by the equation. So you have your W, which is in R E by E. You have A, which is in R of E by R, and then you have B, which is in R of R by E. There. And you can basically combine these weights into a single weight after you're done training A and B by saying W hat, so our new weights are equal to W plus A matrix multiplied with B. So this would give you that those are your old weights and these are your new weights, and then A multiplied by B would multiply along the R dimension, the small dimension, and that gives you your full E by E matrix. Now the idea is that A and B are going to be low rank, and that you only need to have these low rank matrices because the full rank matrix, whenever you're done with your fine tuning, it doesn't need the full rank. It's just not necessary. So you can make it low rank so that you don't have to utilize all the parameters, and since the model isn't going to utilize all the parameters anyways, might as well not make it full rank. Now, once you combine these, then you have your full matrix W hat in R of E by E. And you can also weigh these terms. Maybe you add a little S here, where S is equal to maybe 2, maybe I want to weigh A and B higher. But yeah, that's basic LoRa. Now their now their idea is, what if we use multiple LoRa's, which is a good idea, but how do you do that in a smart way? So they mention this idea in linear algebra. Yeah, let's start with revisiting linear algebra 101. In particular, we are interested in the rank of the sum of two matrices. So this fact right here is an important fact because what it's saying is the rank of A plus the rank of B is going to be greater than or equal to the rank of the matrices added together. So basically what you can do is you can add, so you can have matrix A and matrix B, and whenever you add them together, then the rank will be either less than or equal to the sum of the ranks. So I have an example that kind of shows how to kind of show this idea. So if I have this matrix here, so matrix A is equal to 1, 1, 0, 0, and I have a matrix B which is equal to 0, 0, 0, 1, and this would be, so this rank is equal to 1 because you only have one. You basically only have one vector in here that's linearly independent. So normal linear algebra, same thing with B. And whenever you add these together, then you get this matrix here, which is 1, 1, 0, 1. And this is basically 1, 0, 0, 1. If we're just looking at the linear independent vectors, so that would be a rank of 2. Now, in this scenario, we have the rank of A plus B, and then we don't know what we have here, and rank of A plus rank of B. So, I mean, these are obviously equal because you have 2 is equal to 1 plus 1. I mean, obviously. So that's your rank. You basically have this full, or you've basically increased the rank of your matrix using 2 lower rank matrices. And this is the property that they mention. But they also mention that you can't do this if you just have a multiplicative property. Let's see. Yeah. They say here that R is equal to, LoRa implementations are restricted to the rank. R is equal to the max of the rank. So in this case, A and B, if we multiply them together, since LoRa is multiplicative, so A at B, that gives you 1, that gives you 0, 0, I think it's 0, 1, 0, 0, which is a rank of 1, because you only have one linearly independent vector. And this is the case for all matrices. If you multiply them together, then the rank cannot be higher, but if you sum them together, then the rank can be at most the sum of the ranks of the individual matrices. This is the property they want to leverage. So basically, all they do, basically the idea is, well, what if we start with, let's say we have some number of epochs, and we start with our original weight. So this is epochs. Maybe this is 0, and this is 100,000. It's a lot of epochs, but whatever. So we start with our original matrix, W sub t, or what do they call it? They just call it W. So we start with our original matrix W, and let's say we initialize 2 new matrices. So now we have WA and WB. So we have new LoRa matrices. And let's say at step 10,000, we basically combine these matrices together. So now W is equal to W plus WA dot WB. So we combine these matrices together, and then we create 2 new LoRa matrices, W hat A and W hat B. And then let's say at 50,000, we then combine these matrices again. So then W is equal to, in this case, it would be W plus WA, let me zoom in a little bit, WA dot WB. So this is our old at 10,000. And then we add the new matrices, W hat A dot W hat B. And then you keep going, and you keep adding these LoRa matrices at select intervals. And this leverages the property that, well, because you're adding these matrices together, then if these matrices are kind of constructed right, and if the model plays nice with the matrices, then the rank will start increasing. So rank will start increasing, and it'll never decrease. So because you're adding these matrices together, so the rank will keep increasing, and that is their idea. And hopefully the model does that. So they mention that here, if we could restart LoRa, meaning we merge WA and WB during training, and reset the value of these matrices, we could increase the total rank of the update. So yeah, you have your LoRa 1 and then LoRa 2, and you keep on adding more LoRa matrices, and it leverages this property. Yeah, where the sums are independent enough, meaning that the ranks are going to be the ranks of the added LoRa matrices are going to be higher than the previous rank. But then they mention, however, implementing restarts is not trivial. In practice, requires certain modifications to the optimization procedure. And so you can do this. You can just say, okay, I'm going to add these two matrices here. But the problem is that whenever you add these matrices, the optimization is basically just going to optimize these matrices like it was optimizing the old matrix. So it's not gonna add very much. Basically, the trajectory kind of stays the same as you, like whenever you add these matrices, since you haven't really changed the optimizer at all, the alarm's going off. Yeah, basically since you haven't changed the trajectory, the model is still going to optimize in the same kind of path, in the same direction. And since the model is optimizing in the same direction, adding these matrices isn't going to really help very much. So like I have this amazing diagram here where you're basically optimizing, you're going down to this local minima, and then you restart. You restart here, and you add your new WA and WB. But since the optimizer has the moments, the atom optimizer has the first and second moment, and they kind of affect a lot of the optimization. You continue going in the same direction, which isn't very helpful. If you're going in the same direction, then you're gonna basically end up in the same minima. It's not going to do anything. And they say here, let's assume that the reinitialization boundary W1A and the corresponding gradient momentums are full rank. Then after merge and reinit, continuing to use old gradient moments will guide it to the same direction and optimize the same subspace. So that's a problem. Now let's say to resolve this issue, they propose ReLoRA. ReLoRA performs a partial reset of the optimizer state. During the merge and reinit it sets the learning rate to 0 with a subsequent warm-up. Specifically, we set 99% of the optimizer state values to 0 and use a jagged cosine learning rate scheduler. So basically, they do a few things. First, they set the learning rate to 0. Then they have a warm-up, so we can see here. Let me erase this. So this is your initialization. This is your initial warm-up. And you can see once it gets to this point, this is their reinitialization. So at this point, they drop the learning rate down to 0. Now the learning rate is down to 0, and then they add their new LoRa matrices, WA and WB. So they add these two matrices, and they slowly have a warm-up. I guess it's not that slow, but they have a warm-up. Instead of going directly from 0 to, say, in this case, like 0.97 or something like that over here, then you do a warm-up to that point. So that's the first thing they do. And the next thing they do, which I think is more important, is 99% of the low magnitude optimizer state values to 0. So they set a lot of the optimizer values to 0. So you can kind of think of this as you have your momentum, you have your moments, you have your momentum kind of guiding you, and I kind of think about it this way. So if I have this kind of hill right here, let me erase some of these. So if I kind of have this hill right here, and I start going down, and then I stop here and I do a reset, then let's say I kept my momentum, then I would continue going over this slope here. So this is with momentum. However, what if I got rid of my momentum? And let's say there's like some gradient going down this direction as well. So it's kind of like a hill where I could go over this bump here, or I could go down the side here. Kind of hard because it's not 3D. Let's say I remove my momentum. Then the gradient would be going down this direction here. So you kind of change the path of the optimizer so that you actually utilize the weights that you are given. It's not going down to the same trajectory, rather it's going down a different trajectory. And that's kind of how I think about this. And I think that's why they reset it. I think there's also proofs that kind of show resetting it make it better. They don't have that in here, but I think it's in other papers. And the last thing is they use a jagged cosine learning rate scheduler. Now they add all these and then they have ablations showing that they do improve. But yeah, they basically say we can't just do this. You also have to do some stuff to the optimizer and do some smart learning rate scheduler stuff, which they mention here. So that's what they do. And you may be thinking, well, if we add these LoRa weights, isn't it going to be more costly since we still have since we still have the old weights? So we're basically, instead we're going to have e squared plus 2e weights. Well, not exactly. Now, there's two things that kind of guide how many parameters there are. So if I have, say, R, say I have this W matrix and R of E by E. I'll write it down here. So we have this matrix R and E by E, like this is W, and the amount of parameters you have to store. So whenever you're looking at the bytes in memory, you don't just store one byte for. So if so this is an E by E matrix, and you don't just store one byte for each parameter. So for parameter 1, say this is parameter 1 by 1, then you don't just store one byte. You actually store maybe 2 bytes or 3 bytes or maybe 4 bytes. And if you store float 4 bytes, then that would be a float 32. So this would be a float 32, which is what is usually used for training. However, if you quantize this, which is what ReLoRA kind of did, then you just have to store one of these. So you can make this 4-bit, and you just have to store one of these. So instead of storing e squared, 4 times e squared parameters in memory, you instead just store e squared parameters. However, whenever you're doing the optimization, you have to store the full 4 by e squared parameters. Let's just say you do. So basically, what I'm kind of trying to get at is your frozen W matrix here, this matrix here, this will only take up e squared memory, while your A and B matrices we'll store R by E. Well, if R, let's say R was 1, then it would store 2E. Yeah, that makes it easy. Then it would only store 2E, and then you have to multiply that by 4 because you're storing it in a float 32. Float 32 precision. So if I were to just train W, so let's say I don't have the lower layers, then that would be 4 by E squared bytes in memory. So this is very large. However, if I were to freeze this, so if I have ReLoRA, so ReLoRA is basically saying we combine these, but you freeze this, and this is our normal. Sorry, I just want to write this out a little bit better. So our normal would be 4 by E squared number of parameters, while with ReLoRA, where you freeze W, and you have these LoRa A, B matrices, then this would be E squared plus 2 plus 4 times 2E. So this is definitely smaller, and if you do this for a whole transformer for all linear layers, then the magnitude definitely increases. So all that to say, since you don't have to store you don't have to store W in full precision because you're not training W, you're only training A and B, then this helps a lot with memory costs. And if you have a small r, which I don't know what their r is, but if you have a small r, then it's even more efficient. Now, that's not the only thing. You also have to store your moments for W. So for W, you have to store your moments, which would be kind of a full. So you have to store a moment for each. You have to store the first and second moment for your atom optimizer, which would be one value for each of the weights. So you can see that that's very massive. And your moments, so moments for normal. So if you just train W, if you train W normally, then the moments in your atom optimizer would be 2 because you have the first and second moment, and you're probably storing those in float 32, 4 by E squared. And the same thing again. So ReLoRA, if you so you still have to have W, but you don't have to store the moments for W. Then instead, you only store the moments for A and B because you're only optimizing A and B. Then the number of parameters that you need would be, well, these are your moments. So this would just be 2 times 4 by 2e, or 4 by 2e, sorry, 4 by 2e, because it's 32-bit precision. So you can see that this is definitely a lot smaller still. So 2 pluses, you don't have to store your moments for your full rank matrix. And the second thing is you can quantize your full rank matrix. And finally, yeah. Oh no, those are the two things. Yeah, you can quantize W, and you don't have to store the moments for W. So the two very nice properties, and that allows you to reduce your memory footprint a lot. And yeah, that's what they mention here, just to show that these properties do hold, then that it is actually smaller if you choose R correctly. So now they go into the experiments, and I guess I can kind of show this optimization procedure. So first, they basically just have their linear layer, and notice how the linear layer, they just replace with ReLoRA, where they have their original weight matrix here. So you basically initialize this random weight matrix, and you're not going to optimize it. It's frozen from the beginning. And then you initialize an A and B matrices, so your LoRa matrices from the very beginning, and these are your initial LoRa matrices. Now, as you're iterating over the training steps, and you're updating your parameters, so train step with ReLoRA, then you keep on training these A and B parameters until you get to Q. So Q is the number of steps until you replace your LoRa layers. Now you merge the weights, so this combines the weights you were optimizing, and then you initialize new weights. And remember, in the initial LoRa, or in the regular LoRa paper, you have your A matrix initialized to a random matrix, and you have your B matrix initialized to a zero matrix. And the reason you do that is so that your new weights are not affected at all, or your old weights, W, are not affected at all by these weights, since you have a zero initialization, and the output of this is initially going to be zero, while the output of W is going to be Y, whatever that may be. So you add these together, and you get Y. And this slowly gets changed over time. Now, they also do this pruning. So here, right after you add your new weights, you have to prune the optimizer. And remember what they said up here. They said that they do 99% low magnitude optimizer state values to zero. So they reset a lot of these values, which is what makes the optimization work, as opposed to it going in the same direction. And then they start the warm-up. So that's what you can see up here again. So you have your initial warm-up, you keep going, and then this would be Q steps. This would be another Q steps, another Q steps, another Q steps, and another Q steps. You reset it, and you slowly do your warm-up. So this would be 0 learning rate, and you slowly warm up until you get to however many warm-up steps, maybe 50, 50 to 100 steps, 50 to 100 warm-up steps. And this seems to work well for them. To get even more performance, they put this in bfloat 16 and use flash attention. So they train their whole model in bfloat 16. And one more thing I do want to point out is that they have some kind of obscure like architecture designs. They use RMS norm, SWI glue, and I don't know. I've never seen these. I mean, I've seen them. They're just kind of obscure. They're not the normal stuff you usually see. So it's kind of interesting. Now let's just get on to the results. So basically, all you're gonna do is do multiple LoRa's and you reset your optimizers so that they change trajectories while you're optimizing them and they don't go in the same trajectory and you get useless weights. That's all they're doing. So if we go down here, they say they initialize ReLoRA from a checkpoint of full training at 5,000 update steps and reset it every 5,000 steps. For 3 total times. After each reset, 99% of the optimizer state is pruned based on magnitude, and the loss is warmed up for the next 100 iterations. So they set Q equal to 5,000, and they do 3 LoRa update additions. Now, let's just go to this first chart, which I do find funny. They say that their results are resented in table 2, so in this table, keep in mind, they're resenting their results. No, I'm kidding. They forgot the P, but I thought that was kind of funny. That they kind of forgot the P. But anyways, yeah, if you do full training, so compared perplexities between baseline methods and ReLoRA, control has the same number of trainable parameters as low rank training. Low rank training in bold. So low rank training is bold if it outperforms the control baseline. So yeah, you can see that compared to the control baseline, I mean, ReLoRA does a lot better than LoRa in general. So it's a plus, but it doesn't do as well as full rank training right here. So lower is better because this is perplexity. Yeah, perplexities. So you want lower perplexities, and you can see that it outperforms the control model, but it's still like it doesn't reach the full training, especially at 350. You can see it. Like, it kind of does at 250. And something interesting is the perplexity doesn't decrease when you go up to when you go from 250 to 350. So I'm curious, does this scale? Does this method scale at all? And I don't know. They don't test out more than 350 because of they said they had hardware constraints. So yeah, it doesn't increase. They don't. We don't know if this actually scales. Do scaling laws apply to this method? So something that you want to keep in mind, because it's something that you want to look at. If it doesn't, then this method may have to be improved. But yeah, something interesting to look at. Now, they also look at the singular values, singular value spectra of the weight difference between ReLoRa and LoRa. So you can see the singular value kind of distribution for ReLoRa is it's more similar. So it's the dark blue to full rank training, which is the lime color, than normal LoRa. And they note that there's a lot of zero singular values in normal LoRa, but in ReLoRa it's a lot larger of a distribution. The distribution for LoRa is kind of weird. It's a lot of zeros and then it kind of fades off. Yeah, it's very kind of a weird distribution, but yeah, you can see in general the distributions are somewhat more aligned between ReLoRa and full rank training. It's definitely better than the normal LoRa. And yeah, so that's an important note they make. Now let's go down here to the ablations. So if we look at the ablations, this is, so if you just have nothing, like you just do your LoRa resets, then this is the perplexity right here. And if you do restarts, then the perplexity doesn't really change. So if you do if you just restart, and I think you do restart with, I think it's just restarts. So I think this is normal right here. And this is if you restart with ReLoRa. So this is with your ReLoRa, then it doesn't really change. Yeah, I think this is normal LoRa. And this is your LoRa with restarts. Whatever. LoRa with your changing weights. And you can see it doesn't really change very much. It doesn't add anything because it's kind of going in the same trajectory. Now, I guess if you have the optimizer reset, where you reset the optimizer values to 0, or most of them, then it doesn't even finish training, I guess. That's why they have NA. And if you add the jagged scheduler, then it does pretty bad still. But it starts to get good once you actually have, so it's kind of two things that improve it. If you have all three of these, then it improves it. And if you just have the warm start, so if you don't even do restarts, and you just have your warm start here, so instead of starting at, say, this is your learning rate, since percent, and say we 100%, 0%. So if you just start at 100% at epoch 0, then that's a lot worse than if you do a little, like a warm start. So restarts and warm starts are essential for good performance, which is interesting. And if you have all four of these, then it does really well. But you can see that if we just look at the restarts, or the normal LoRa, and you just look at the one with the warm start, it does a lot better. And if you add the restarts, jagged scheduler, and optimizer reset, you get even more performance. And I guess if you that causes it to diverge. So yeah, that's what we have. And they mention here, ReLoRa without a jagged scheduler optimizer performs similarly to LoRa because old optimizer states force newly initialized parameters into the same subspace as prior weights, limiting the model's capacity. However, doing a naive optimizer reset causes the model to diverge. A jagged scheduler helps training and has a positive impact. So you kind of want to find this middle ground between it totally diverging after you reset it and it totally not changing its trajectory at all. So that's why you have to have both of them. And do note that this value down here versus this value, this value right here does not use the restarts, so it's probably just normal LoRa, and this value right here is ReLoRa, so kind of similar, kind of an interesting thing to look at. And yeah, this is just also saying the singular value. And yeah, so this part right here is an important note. Scaling beyond 350 million due to limited computation resources, they don't train beyond 350 million parameters. But while it does outperform the control baseline, the trend does not increase. So we attribute suboptimal hyperparameter choice, which requires further investigation. So they claim that they chose suboptimal hyperparameters, which made, so if we go back up here, which made these scores very similar. The score for 350, well, not similar, the same. You would expect this to decrease with scaling laws, and they say that's due to hyperparameter choices. We don't know yet, so that's something that's interesting to look at. But yeah, overall, that's the paper. Just basically doing a reset while you're resetting while you're training LoRA, as opposed to just training your entire model using a full rank matrix, or just using LoRA one time, and you can see it kind of improves it. So there you go.